colloquium we have every month, the so-called Directors Colloquium. And today I think we have a very interesting one that is related to the management of scientific data at the EXA. And in fact, we have two speakers today. One is coming from the Netherlands, from Astron, but he will be talking about SKA, that it will be the world's largest radio telescope at the beginning of the 20th. On the other hand, we have the second speaker that he's coming from CERN, and he will be talking about the LHC, and that is the largest particle accelerator. Then we are dealing with two of the most important infrastructures, scientific infrastructures for the next years. But in fact, what they share is that they are really the largest producers of science data in the coming years. Just to give you some numbers, the CERN has just surpassed the 200 petabytes limits for raw data in the last months. And just to give you another number, is that the high luminosity LHC will exceed this limit every year. It means 200 petabytes per year. On the other hand, SKA, already in phase 1, that is only 10% of the global project, will store something like 300 petabytes per year. Okay, then it's really a big challenge. In that sense, in July 14th, and this summer, an agreement was signed between SKA and the CERN in order to work together in big data. Okay, it has signed a contract for big data cooperation. And the idea was just the identification of joint challenges in approaching exascale computing and data storage. What is clear is that with these new facilities, what is going to change for sure, and in fact there will be a fundamental change in the way that science is done. And I think after the seminar today, we'll have a clear feeling about it. Okay, let me then just welcome our two speakers, and then Lourdes is going to introduce both of them.
Thank you, Anton. I'm going to be very brief because I'm not in a very good shape today. In fact, I'm going to sit. Sorry. I'm going to be brief because something we do is we circulate a summary of the CV of the speakers, so it doesn't make sense to go into much details about that. As Anton said, SKA is going to change the way we do science from now on, and this is why I think this is a very exciting week here, because this week is about these centers that will allow to change the way we do science. And not only for radio astronomers. And the proof for that is that we have here two people, one radio astronomer, but with a very large range of multi-wavelength work, Michael Wise, who is the head of the astronomy group, but also Ian Bird, who comes from the CERN, and his background is particle physics. And so it seems that we are going to face together challenges that can improve or can be helpful for any, I think, not only astronomy but scientific discipline. And so the challenge is not to store, to transport, not only to deliver the data, is really to do and extract good science from them. So this is, I think, why we are very excited this week. I hope I will enjoy better the rest of the week, but today we have the meeting of the Regional Center Coordination, SCA Regional Centers Coordination Group. Tomorrow we have SK Link meeting, and then we will have INEA's plenary meeting on Wednesday and Thursday. And there's another meeting on Friday, so, well, you have all this information. So I think I prefer that first Michael and then Ian speak.
Oh, so thank you, Lourdes. I especially appreciate you coming in today and giving the way you're feeling. So my talk and Ian's talk actually go together really well, which is a bit strange if you think about it, because as Lourdes just said, I'm a radio astronomer working at the Netherlands Institute for Radio Astronomy. So in some sense, I'm coming at this from the perspective of an SK user. How can I use the SK to do science? And Ian is, of course, a physicist, and he's trying to get science out of his experiment as well. But it's really a common problem because underneath the hood, as I go through my talk and as Ian goes through his, you'll see there's a high degree of commonality, especially at the scale and the sort of generic issues of how we make this much data available to scientists to actually do their science. You can think of a data infrastructure that is large and is potentially usable by a number of communities, and then we have our domain piece that has to sit on top of that. So I'm also the EC coordinator for the Aeneas project. I'll talk about that a little bit in passing, but I'm not here to talk to you about that project. I'm here to talk to you about this challenge. I'll say a little bit about the SK. I know not everybody in the room is necessarily a radio astronomer. And specifically, I want to talk about how we put an infrastructure in place that lets us do science with the SKA. And I say a platform for global astronomy because it's not just about centers. It's not just about buildings with disks and software. It's about a platform where you can do your work and do it in as close to possible a way as the way you're familiar with doing, but at the kind of scales that we have to struggle with. So I'll say a little bit about the SK and just data-intensive astronomy because this is not a radio problem. Radio telescopes at some level are pushing the boundaries. They're at the sort of forefront of this challenge, but it's a generic challenge. And you can talk about LSST and other instruments that are also going to have similar challenges soon. So SK is a great motivator to face these challenges head on. I want to talk a little about the global infrastructure, and it is a global infrastructure that we're trying to put in place. There are some challenges and boundary conditions. Obviously, we don't have infinite resources to solve these challenges. And then again, I'll end with saying a little bit about Aeneas, which we're going to, of course, have a meeting, for several days toward the end of the week. And I know you've heard about some of these things before. So I'll just start by, sort of drawing a line under this point. It's a great time to be an astronomer. These are all instruments that are available or soon to be available or coming not in the not too distant future. And although that's great from the perspective of having all of these instruments and all of this data available to do your science, they all generate an incredible amount of data, especially as you move down this way into this regime and things like LSST and CTA to come. So takeaway messages, although I'm going to talk a lot about the SK and about radio astronomy, these other telescopes are hard on our heels and they also have similar problems. So in some sense, we need to come up with a solution that will work for multi-wavelength astronomy. So I don't want to spend a lot of time on this, but I think this, as Anjan said, we have to look at changing the way we do astronomy. I think most of us are already involved in large international collaborations. We're dealing with increasingly large data sets. We have to coordinate all that. And it's tough, and it actually slows down scientific results coming out. We've certainly learned that the hard way with LOFAR, which is a telescope that we've been building in the Netherlands and here in Europe. Just the sheer complexity of those collaborations and that data combined slow the output of science. If we slow the output of science, the arguments to our funding agencies for why we need these infrastructures is weakened. So we have to get science out of our telescopes. And the real point here is that we are already at the petascale. I'll show you a slide in a few minutes. We already have over 30 petabytes just of radio astronomy data. I know that's not quite as impressive as the CERN collection, but we're well on our way, and that's from one telescope. And there are a whole bunch, of course, that are just about to break out with Meerkat and ASCAP. So we're already at the petascale, long past it, and we're rapidly approaching exascale. And we're already facing bottlenecks. So that's the challenge. And the question is, how do we meet that challenge? I wanted to, again, make the point that it's not just radio. There's a lot of radio here, but there's a few others. I just want to give you some context. Once upon a time, SDSS, the Sloan Digital Sky Survey, was the big data challenge of the day. It generated something like 40 terabytes total in the first few iterations of its data release. Of course, we take that much data in an evening now. LSST is the sort of natural successor. and it will generate, again, a lot of data, but not even particularly scary by our current standards. Scary in the sense of actually doing something with all those petabytes, but these are no longer big numbers. And then, of course, LOFAR, as I said, LOFAR routinely generates hundreds of terabytes a night, depending on the type of observation, and our archive is growing between 6 and 10 petabytes a year. So this is what we're struggling with today. MWA, not so dissimilar. And these are all just about to come online, well, just about over the next few years. 2020 is not that far away. So you have to keep that in mind. And of course, SKA, as I'll show in a bit, is going to push us into the exabyte range. So not a radio problem. And just to give everybody due time, of course, it's not even just observational data. Numerical simulations have traditionally been separated from this discussion about data collections, but in fact, this is just another kind of data. These are obviously large scale, the Millennium simulation and follow-ons from that. Having access to that data in a uniform platform is something we would ultimately, of course, like to do, because all of that data has to be, matched against these kind of simulations to try to figure out what they mean. So again, just trying to make the case that we're looking for a solution and a platform that can bring all of these different kinds of data together and let the user pull together whatever they need to do their science. So again, I'm going to talk about the SK a little bit, just because that's what I'm trying to sort out at the moment. The SK is a global project. It has 3 sites. It's a telescope and 1 observatory, 3 pieces. We have the office in Jogga Bank here in the UK, and we have 2 telescopes in the western desert of Australia and in South Africa. These are the countries that have already signed on to be members, or intend to sign on, I should say. And of course, there are other countries, including Spain, happy to say, who are interested in joining, and we hope will yet join. So we're moving ahead with this group to try to get some of this sorted out, but of course we want participation from as many countries, especially in Europe, as we can. So it's truly a global project. The science, I'm not going to talk about the science per se. The science drivers for the SKA are large and ambitious and transformational, I guess if Phil were giving this talk, he might say. These are a sort of rough breakdown. You can break it down in different ways. I guess the point I would make is these are not so different. If you looked at the high-level science priorities for Athena or the LSST, they map to these kind of questions as well. So although these are the science drivers for the SKA, there's a lot of commonality. And it is to solve any one of these questions, you will in fact need more than just SKA data. The SKA will not solve these problems just by itself. Again, I don't want to spend a lot of time on the SKA, but I just want to show you some pictures. So again, we have two sites. One is in South Africa. This is SK Mid. So this is the L band, or the hydrogen line. And I don't know if you can read this from here, but the main thing I would have you see is that the raw output of this telescope, just this piece of the SK, is huge. Now, 62 exabytes a year, okay. We're not going to save all of that. That's not the intention. The intention is that that raw data will be processed by the observatory in the science data processor down to some set of initial data products where the scientists will actually begin their science. But in some sense, this is the level of data that the observatory has to deal with, and it is, of course, very large. Now, similarly, we have the lower frequency component of the SK, which will be based in Australia. These are examples of some of the dipoles, prototype dipoles for that component. This is similar in some level to the phased array technology we use on the FAR. And here's an even crazier number. I don't know if you can read it, 4.9 zettabytes. Again, those are just big, scary numbers to be impressive. That is not what the user is going to have to deal with. That's what the observatory is going to have to deal with in something like real time, because we can't store it. What that translates into the system data flow is that we expect to have to translate all of those petabytes, exabytes, and zettabytes into a series of derived data products, which we don't have an exact number for, because of course you have options. What science data products you derive is something that you have some flexibility. You can have a minimum set, which is designed to only achieve the scientific priorities of the telescope, or you can have a sort of more general set of data products which allow you to do more science, a discovery archive, if you will. And so that's why there's a bit of a range here. So that's a free parameter we can play with. But of course, in the end, we want to generate as much science out of the telescope. So for now, we're assuming something toward the upper end of this regime because we want to get more science out of the telescope. So the number I would have you take away is this 300 petabytes a year. That's the size of actual derived data products where you will begin your science. And that's what needs to go into the archive. And just to put that in scale, a little bit of scale, so these are some other big data producers. Hope I got that number right, Ian.
I have the same size.
Okay, good. So this is in petabytes a year. So here we are today with LOFAR generating 7 petabytes a year. CERN is definitely beating us there. But this is where we're going in the not too distant future. 2024, again, not that far away. So 2024, at least based on current schedule, is when we expect the first phase of SK1 to be complete and full science operations to begin. We'll, of course, start sooner than that. If construction starts in 2019, as we hope, this is going to ramp up steadily from nothing to 300 petabytes each year. So we don't have that. The takeaway message from this is that we don't have that long to prepare for this level of data. And again, this is phase 1, and ultimately SKA phase 1 is intended to be roughly 10% of the full telescope that we will continue to work on in the coming decade. So we start at an already scary and impressive number, and it just grows from there. So this is the infrastructure that we need to prepare to receive this data, because that data is actually where you do your science. And this is a slide I like to show. I especially like to show this slide to funding agencies, because I'm sure everybody in this room has used an archive from HST or Chandra or XMM, and archives are great, and they let you do more science, and that's the argument we always make. And this is actually a plot from HST, which shows the number of publications that were generated by data that HST took. And so somebody proposed, that observation got taken, it went into the archive, they wrote a paper, somebody else came into the archive, got that data and wrote another paper. And so the blue is what you get if just the PI writes the paper they said they were going to write. And all of the rest of this curve, which is a factor of sort of 3 more, is what you get from other people coming to the archive with a different idea and a different project. And the point here is that you get that multiplicative factor that in terms of the total amount of science, but you only get it if a couple of boundary conditions are met. One, the data has to be there over long enough time for people to come with their new ideas and find it and get it out. The data has to be in a form where they can do other science. I mean, if your data product that goes in the archive is too specific, that might limit somebody else's ability to do additional science, so that's where that discovery archive is useful. You pay a little bit for it in terms of what you have to store in the infrastructure, but you get the science benefit. And this point in particular is the really important one. It assumes that you can actually do something with the data. With HST or Chandra or whatever, that's easy, right? You download it to your laptop and you do your stuff. You write a paper. Well, if that data that you're downloading is now hundreds of terabytes or a petabyte, well, you see that boundary condition is broken, and you don't get that multiplicative factor. So you can store all the data you want, okay? But if you can't provide, if the community or the users or the observatory or somebody can't make that last boundary condition true, you don't get this multiplicative factor. In fact, you don't even get the blue. So the point here is that this infrastructure that we're talking about is absolutely crucial to the scientific success of the SK. So the way that we envision making that boundary condition true is through a series of what we call regional centers. The regions mean geographic regions, roughly speaking. Europe is a region, China is a region. And these regional centers will provide access to that 300 petabytes a year of initial data products where you actually begin your science. But they will also provide access to the computing resources and the software stacks and the tools to let you begin to do your actual analysis. So it's a bit of a, and of course they also do things like provide support as well, expert support for the telescope. And this is a different model. So this is no longer I get to download it to my laptop and do everything in my office all by myself. You now have to come to the platform and bring your science goals and your algorithms and your scripts and whatever to that platform. And so part of our job is to make it possible for you to do that. You have, it would be a mistake to say that the science data centers are going to do everything you need done. We're going to provide every tool and every script and every documentation and so on. That's not the idea. The idea is that we provide a platform, we provide some tools, obvious ones, things that we can foresee, but we need a generic enough environment where things that we can't foresee can still be done. So that's at least the ambition. And again, the point here is that for the most part, this is where SK science will get done. Not in your laptop, not on your local clusters, but in this environment. Now, your local clusters may in fact be part of this environment, ideally. So, of course, these data centers, this is trying to make the point that this infrastructure is not just for radio astronomy. It's actually, the very nature of the scale of what we need precludes that it be only for SKA or radio astronomy. It has to be more general. And just to make that point, that infrastructure, this science data center, once it exists, is useful and should be useful and has to be useful for radio astronomy and optical astronomy and X-ray astronomy and even beyond astronomy. So it's a place where you can support multiple data collections from multiple instruments. You can provide user support for all those instruments, not necessarily in some monolithic group, but it's certainly a place where that user support can focus to provide support to the community. It's a place where you can have academic partnerships, both with universities or nonprofits or what have you. And it's, of course, also a place where you can reach out to industry and technology developers and even different research communities, which is, of course, Ian's going to make that point for me in a moment. So it's a platform, and keep saying that. And the clicker seems to have stopped. So what does it do? Well, this is not intended to be a sort of definitive list. This is an example of some of the things that you can expect to find in any analysis system. So you have to be able to, of course, discover data. The data is there, data is available, not just for your telescope, the SK, but also for others. So this is where the VO and the IBOA work is definitely leading. You have to be able to do data processing, maybe some version of the processing of the observatory data itself, but also rerunning those pipelines, but with different configurations for expert users. And finally, you need this analysis environment where you want to interrogate the data, and perhaps you want to correlate it with other data from other telescopes, and again, in an interactive way, or at least semi-interactive, because this analysis piece is the part where I don't know what you want to do, and you don't know what you want to do. We all of us who work with data know that you sit in front of the terminal and you look at what you see, and based on what you see, you take the next step, and you didn't know what that step was exactly going to be before you took it. So we need to preserve that at this scale, and that's a little bit different, I think, than the high-energy physics community. So one of the things that we're looking at, this is a slide stolen from the LSST, which again highlights the point that these ideas are something that the broader community are wrestling with. Given all this data, how do we bring our users to the data and let them bring their analysis, which we don't know beforehand, to that data? And so this is a sort of schematic of the sort of design where you have a sort of generic infrastructure where that data is stored, disks and compute. And then on top of that, you have a software stack that is specific to your telescope, perhaps in the form of some sort of container or a package, so you don't have to try to reinstall complicated pipelines and what have you. And more importantly, The portal is where you do your discovery and you find out what's in there, and you define the data that you want to access. And once you have, you can use something like a IPython notebook or Jupyter Lab notebook, as it seems to be called these days, to bring your script to that environment. So this is, it's so fun. You know, I saw this presentation by the folks, the development team from LSST, and I said you could just change the name, just cross out LSST and write in SKA. We're doing exactly something similar. I think those of you who are around the rest of the week, Rob Simmons will show something for the folks at IDEA in South Africa are developing a very similar platform. We've installed that platform in Astron. So this is, at least to first order, what the community is experimenting with to bring users to the data. And this is just an example, at least from the perspective of SK. This is the kind of analysis a typical sort of analysis that a radio astronomer will want to do with one of the H1 cubes from SK surveys. The difference is, of course, that cube in the SK era could be huge. It could approach a petabyte. And going through and identifying all of these little blips by hand and saying which one is real and which one is an artifact is not something you're going to do by hand in a petabyte cube. So we need a way to automate, you know, design, test, prototype, see if it works, and then automate. And you need a platform that lets you do that, because ultimately you're not going to go through a cube this big and do each of those identifications by hand. You need automation and tools to help you with that. So you need a platform where you can define your analysis, and then you need a platform that lets you automate it once you have. So we have a couple of open questions that we have to still address. Where will that 300 petabytes a year, where's it going to go? Where's it going to be stored? How will it be transported to Europe? Because it won't all stay in the deserts of South Africa or Australia, so it has to go somewhere. We're assuming some subset of it, if not all of it, or at least one copy of it will come to Europe. How do we make that happen? This infrastructure is big enough, I said before, that we're not going to be able to go to the funding agencies and say, hey, radio astronomy is really awesome, I need 100 million euros a year, please, because they will say no. So we have to use the infrastructure that we already have, and there is a significant amount of HPC, storage and computing infrastructure out there already. We probably need to see that it grows, but we definitely have to take advantage of what infrastructure is already there. We need to know how we do all that. I'm standing up here waving my hands and talking about this flexible platform where there's a lot of technical stuff underneath that astronomy layer about managing, you know, and computing and processing 300 petabytes a year of data. So what tools and interfaces and techniques do we need to do? I mean, we've made a start. We're looking at certain solutions today based on the data we have from the precursors and pathfinders, but of course that's we don't have all the answers yet, so we have to look into that. And finally, how do we set up and operate that sort of global network of HPC centers and set that infrastructure up in a way so that you, the astronomer, doesn't have to care. You just want to find the data from some H1 survey that SK took. You don't want to care whether that cube is in South Africa or is in Canada or is, you know, in Europe. And so we need to figure out how to set up and operate that infrastructure so that you don't have to care. So these are all questions that, finally I got to Aeneas. So these are all some of the questions that we're looking at within Aeneas. Aeneas is an EC project. It was funded by the EC. It involves 13 countries, 28 different partner institutions, and we're looking at all of those challenges. So we have a number of work packages. I don't expect that we'll solve them all, but we are looking into each one of those. And at the end, it's a 3-year project. We're 10 months in, and the idea is that at the end of that 3-year project, we're not going to build that infrastructure. We're going to present a design to the EC for how we think we'll set it up with the infrastructure we have, with the tools that we've examined, and with the governance model that we will propose. And the idea, of course, is that we hope at least that the EC and the national funding agencies will say, that sounds great, let's do that, and sign on as part of the operation and the scientific exploitation of the SKA. And so this is what we want to set up within Europe. Again, Aeneas is looking at at the whole problem from a European perspective, but some of it, of course, is not European. The technical issues and the international governance, those are not specific to Europe, but our ultimate goal is to make sure that Europe as a region is part of this global network. So we need to coordinate ourselves within Europe so that we can, interface with our international partners in South Africa and Australia and Canada and China and so on and so forth. And this is, of course, what we're ultimately shooting for. We want this to be a global network. These, again, are not fictitious points. All of these regions have expressed an interest and are actively working to host an SRC and to be part of this, again, this seamless network of regional centers. And it's just, I'm sure, a coincidence that everything sort of comes here to Europe. So this is my almost last slide. So this is a rough timeline for where we are. I think it's reasonably up to date. So again, if construction this year, or this year and early next year are important years for the SKA, this is basically when we hope to get a go, no-go to start construction. I think realistically at this point, construction won't start until 2019. I'm looking to see if Antonio wants to shake me off or just nod. But something on that order is when we hope to start. We hope to form the International Treaty Organization that will build and operate the SKA, and we'll start construction. And that means, again, that early science or the first data will start flowing not too soon after 2020. 2020, it's 3 years. So we don't have a lot of time to get ready to start catching SKA data. So it's a bit of time pressure. But that's well matched to the NAS project in the sense that on that time scale, we should have a design for how we want to do this that we can present to the EC. And at that point, they will have presumably already said, yes, let's go, the SK is great, and we can just proceed to implement it. So I'm going to read these. I think the point here is that this is it's not just a radio problem, it's a challenge for all of astronomy, and ultimately the infrastructure that we're going to need to solve this challenge for astronomy and the SKA is a generic infrastructure, and that's where the collaboration with the high energy particle physics community is really important, because they also need a similar growth in the infrastructure. And I'll hand it off to Ian at this point. I hope that was a good segue. And he can tell you about their perspective. I assume you won't stop for questions?
Okay, so we should use the right slides, I guess. Okay, so I'll give a view from the high energy physics point of view, and I'll try and explain why, well, Michael already did a lot of that, why we have an interest in working together with SKA. So if we start from the beginning, you've already seen part of this slide. I mean, we're both investigating the large-scale structure of the universe, how things work, the origin of the universe, and the very big science questions. I mean, you saw this from Michael. I mean, we're really looking at some of the fundamental questions. Do we get hints for dark matter, dark energy? Can we test the standard model of particle physics? What happened to all the antimatter in the universe? And we're probing very similar scales on the early universe. Is this right? So what I'll talk about, just a few words about the fact that we're both looking at extreme scale data challenges. I'll talk from the LHC point of view what we've been doing to address this so far, how we've set up our infrastructure. I'll come back to the new challenges that we're looking for, and then I'll talk about the synergies with SKA and the collaboration we've put together. Okay, so this is the LHC. You've probably all seen this diagram. So the accelerator itself sits underground. It's 27 kilometers in circumference. The physicists talk about this being a new frontier in energy. For the computing people, it was a new frontier in data volume. So we currently are running at about 50 petabytes of data per year. So this is data that is used to do physics. This is what we call the raw data. This is what's coming off the detectors is actually rather more than this. So the useful data that's generated in the two big detectors, so Atlas and CMS are the ones that discovered the and each buzz, which is about 10 to the 11, 10 to the 11, 10 to the 11, and we collide those megahertz in order to use realistic rates of interesting. And the problem is that you have to keep more or less all of this to get the interesting things out. Now we're starting from a different. So we had collaborations. The collaborations are but together. What interesting thing is that technologies about. So there's an interesting which ran for about 12 years, generated data. Well, for us, through the detectors, was the pixel hit, how much energy was, and that gets reconstructed into all of these. And if you about a petabyte of to afford. Started doing this, first ideas of this. a search engine. Cloud providers at CERN at the scale. Nobody really knew how to do this. He would start from a different place. He would take. Nobody even believed access over the network. People didn't even. Generated at CERN. The bulk processing. This idea that so the tier 1s together with the tier 0 had this role of long-term archiving the data. And then at the tier 2s, which is really the university physics departments, this is where the physicists got hold of the data. And also one of the big compute loads of this whole thing is something like 50% of our computing is simulation. An awful lot of that gets done at those local clusters in the tier 2s. So the scale that we're at today is about 170 different sites in 40-something countries. We're about 750,000 cores, and today we have about an exabyte of storage split equally between disk and tape. And we rely on very fast networking, obviously. So each of these countries, their funding agencies, have made a formal agreement with CERN to provide resources for this infrastructure. So today, as you see, it's really global. We're everywhere in the world. Okay, you already saw this. That was to emphasize the fact that we are also both addressing common problems in terms of global communities, and one of the facts is that it's more than likely that in many places the computing infrastructures will overlap. We will have to do SKA and LHC computing in the same physical location, so we really need to be able to work together for the benefit of the people that are supporting that. Okay, so you already saw the data rates, so they're very similar to what we're talking about, 300 petabytes a year, which will go to the SKA regional centers. So that was where we are today. What we're looking for in the coming years, so we're doing a major upgrade of the accelerator and the detectors, and this is scheduled to be completed in around 2026 or so, which is what we call run 4 here. What this means is that the trigger rates, the number of collisions, goes up by a factor of 10. The total data rate goes up by a lot. I'll explain that in a minute. And also the complexity of the events gets much higher. When we do the collisions, you don't just get a single collision which you read out and process. What happens is that you get overlap in the time slice that you can read out. You get many overlapping collisions. Today, last year it was about 30 that you saw in a single time slice. Today it's about 70 for some complicated reasons. What we expect on this time scale is order 200. Now, that sounds like a linear problem. Unfortunately, it's not. It's an exponential problem. So the processing time goes up, not quite exponentially, but very close to exponentially with the number of overlapping collisions, because it's a multiplicative factor. So this makes things much more complicated and increases the compute load significantly. So what we're currently talking about on that time scale for the first year of this, its upgraded accelerator, is something like 600 petabytes of raw data a year, and around an exabyte for a single copy of the derived data, which is really the data sets that people do physics with. And in terms of computing, we're estimating this is about 20 million cores or so. If you bought them today, it would be the equivalent of 20 million cores. The problem with that is that we think that technology doesn't give us most of that. Technology, assuming a flat budget, gives you about 10% of that. So we're a factor of 10 away from being able to afford what we need to do. So we have a challenge in trying to make things much more efficient and fit within the budget that we anticipate with being made available. We have some ideas about how to do this. This is not completely hopeless, but nevertheless it's a significant challenge. So this is my version of the same plot. So the 73 petabytes that Michael referred to is the total CERN science data per year. So CERN is not just LHC. LHC is about 50 petabytes a year. What each of the experiments is managing, however, is about a data set of about 200 petabytes. So this is all the derived data and the many copies, but they have to manage that and know where they are, which is comparable with what Facebook is doing. And then you move on to the future. So SKA phase 1 is about 300 petabytes a year. We're talking about, this number has a huge error on it because we don't really know what that number is going to be, but it's probably about 500 or 600 petabytes a year of raw data. And we think that turns into an exabyte a year of physics data. And for those people as old as me, this is about 10 billion round trips, which would be very difficult to manage in that way. So we have similar problems on a similar timescale, so it makes sense to do things together. The other thing I mentioned here is the networking. So this, our hierarchy was set up assuming that networking was not very good, that it wasn't particularly reliable, and that we had to replicate things everywhere. That's certainly not the case, but we solved it initially by over-provisioning. And one of the things that we did, we set up this optical private network, which was dedicated connections between CERN and each of those tier 1s. It started off being 10 gigabit connections. Today it's often multiples of that, or even 100 gigabits. We even have about 300 gigabits across the Atlantic, not just for us, but this is we're the main user of that at the moment. And so this really solved the majority of the problem. And then the connectivity between the tier 1s and the tier 2s and between each other, we rely on the national research networking, but we have an overlay on top of that to allow the NRENs to manage our traffic, and actually they discussed charging us for it at one point. That's never happened. So we anticipate networking to continue to develop at a similar rate. So this is a plot over about 30 years, and this is coming from ESNet in the US, but you can see this is really an exponential growth, and there's no reason to suspect that technical growth will stop anytime soon. So we're relying and assuming that networking will be there at the level that we need in the 10-year time frame. So this is just an example of the amount of data that we're collecting. As I said, in 2016, this is the run 1 of the LHC, so these were the first 3 years of data taking. Then there was an upgrade of the accelerator, and you can see the data rates went up. This was 2016, and here we are this year. We're moving data globally, everywhere, all of the time. We have an average rate of global transmission of about 40 gigabytes a second. And as Michael said, we have about 200 petabytes on archive at CERN. And computing is is an important factor, obviously. So again, the compute processing is delivered globally, and here you see just an example of what we are producing. So this was the beginning of the LHC data taking, and this was already a stretch to reach this level. This was a huge amount of computing, and it took a lot of convincing of the funding agencies that we should even have that much. And you can see, in comparison to what we're actually doing today, that was almost insignificant. But nevertheless, so this is more or less the yearly growth. It's more or less in line with flat budgets. It's not, it looks significant, but actually, if you put Moore's law on this, it's not so far off. And then today we're also doing delivery of that compute service in a much different way than the original grid infrastructure that we had. So this is much more, this is based, what we have at CERN is based on OpenStack, so open source cloud software, provisioning either virtual machines, containers, or actually the bare physical machines. But we also connect out to public and private clouds, and also volunteer computing. And this is invisible to the users. That will be the intent. And they basically see this through either through APIs and command lines or through a batch system. And the model that we're pursuing is one of a hybrid model where we don't own all of the infrastructure, but we're likely to buy some of it from cloud providers at some point. And this is just an example. We've been doing very large-scale testing with some of those cloud providers. This is an example of being able to use Google and Amazon at the scale of several 100,000 cores. We've also been doing a project through many different funding agencies in Europe to actually jointly procure cloud services. So this was the first time we've ever done a joint procurement, and that was really to understand whether it was possible. And it certainly is possible, which gives us the possibility of economies of scale in joint funding of things. So the model that we're looking at for the future is actually a bit different. It's more like you would expect from today's commercial computing environment, trying not to move the data everywhere, because this is really a significant cost. So in those numbers I showed at the beginning, we have about 500 petabytes of disk scattered throughout the world, and lots of that is in very small chunks, which is very expensive to maintain, and not so usable because you need a certain threshold to make the facility usable. So rather than do that, we have the idea that we use the networking which we think will be available with a few large data centers and try and keep the data relatively relatively few places, and treat it as a single virtual data center. And we think we can do that these days. So this concept we call a data lake. And really this relies on people accessing the data remotely. Now, as I said, something like 50% of our resources are dedicated to simulation. So I think the fact that we have all of these other computer centers allows us to use those for really strong simulation as data generators. And we also make use of HPC resources. So actually, one of our strategies is to make use of computing no matter what it was. And this is coupled to prototypes now of really remote analysis. So actually, this is very similar to the picture Michael showed of the LSST idea for using notebooks and accessing data remotely. We're also prototyping very similar things. Just a word on software. So we recognize that as part of this factor of 10 that we have to find, the software performance is extremely important. So we actually set up a whole collaboration. We call it a foundation because apparently collaboration has some bad connotations in some areas. To focus and coordinate the community on efforts to improve the efficiency and performance of software. And it's explicitly not just for LHC, because this is really a common problem across many fields. So this is tying together people in our community with other communities and trying to understand how to progress in this area. And we think that this is one of the big ways of gaining some of that factor of 10 back. There's also a lot of effort on other big data tools these days. And the two I mentioned here are the sort of Hadoop style of universe with things like Spark and so on these days. And then machine learning, which of course comes into play in many places. And actually there are some hopes that some of these new algorithms will have significant performance improvements over some of the traditional ways of doing, for example, reconstruction. There's some exciting work going on there. The reason why I mention this is because if you go then back to this idea of doing cloud access to your data and remote processing, this SWAN system, which is web analysis, I can't remember what the S stands for, is really web-based analysis facility in order to make use of those large cloud scale things where you keep all of the data. And the idea is that, I mean, the prototype today is using the analysis system that we have based on root. So it's basically launching containers, which then you access through a Jupyter notebook. And this is then running on the infrastructure. In this case, this is only at CERN, but it can scale out at the back end. And we're also looking at extending that to Spark and other kinds of workloads. Now, the idea is that this becomes more general and that you have access, well, first of all, you have access to the physics data, and then on the back end, you have the possibility to scale out the infrastructure across many different computer centers. Yeah, so this really provides the analysis portal into this kind of data cloud model. So our challenges on the 10-year timescale are the fact that we'll be a multi-exabyte challenge. We really need to focus on driving down the costs, which essentially means bringing up the performance, not just in terms of software, but also in terms of what it costs to operate the whole thing. So this really implies significant changes in our computing models and in the infrastructure. As you've seen, SKA has similar data volumes on the similar timescale, so I think we've seen that there are really opportunities for synergy across here. And I mentioned this, we've been doing this a long time, but if you started today, you really wouldn't start from the same place. So this is an opportunity to look at what we're doing and see whether there's a better way of doing it, and hopefully to prototype some of these things for the future. So this collaboration, recognizing all of those synergies, in July, the Director Generals of the two organizations signed a collaboration agreement on computing and data management, recognizing that both of us have similar interests. The topics within that collaboration are essentially a roadmap to see how we can together look at what we need to do in terms of managing data on that time scale, particularly since we will be working together in lots of different places and in, for example, in the public e-infrastructures that support this kind of computing, and certainly talking to the same funding agencies. Exploring opportunities for collaboration on the common aspects. So, for example, the work on computing and OpenStack is already very active. Last week we had a first discussion where we discussed storage and data management. Working together with the face towards industry, because there's potentially quite a lot that industry can give us in these areas. And then prototyping jointly models of regional centers and different ways of doing computing, and other things as they come up. So in terms of what we think might be in this roadmap, it's really recognizing that we're both infrastructures facing the same challenge. We may be doing it first, but a lot of others are coming right behind us. So we're looking at the period of getting these two infrastructures into full operation, with an eye on the future. Open to other people collaborating, clearly, and doing this at a global level. So we tend to talk about Europe or other places, but really you have to remember that both of these are really global organizations and need to address that at a global scale. So we'll do this through workshops, through prototyping, and through a variety of other means. So specifically on a couple of ideas that we had, one is to really try and use existing science activities to generate real value for the community. So what was mentioned last week was LOFA or HERA. For us, it really means feeding the results of prototypes back into our production systems. We recognize that we can never stop what we're doing and create the new system. We have to continually evolve. So even that evolution may be a significant change. If it brings us a benefit, we'll fold it back into our running system. And then we'll look at exploring concepts for common regional centers, such as this sort of data lake federated data infrastructure idea, and understanding how to mix the compute capacity with that. Okay, so just to finish then, we're both facing the same challenges. There's lots of commonality here. We probably have to coexist together at many regional centres, so this is really an opportunity to do things together and to influence the way this is done for other people and how we talk to other funding agencies. Yeah, thank you.
Okay, thanks to both speakers for the very interesting talks, and we'll have some time for questions. Enrique.
Yeah, you mentioned that the naive preparation for storage means for a tenfold shock of the actual storage available for the current technology. Are you exploring, is there any, under the new storage technology will be mature enough to make use of something that will bridge this tenfold gap or whatever?
Technologies coming, but none of them look as though they will be competing with physical tape on this timescale. We make big use of tape, not just for archive. We actually keep active data on tape and move it in bulk onto active storage when it needs to be processed. So this is really automated but organized way of using the tape systems. It's not just a cold archive. There is nothing which really looks as though it's coming at similar costs. And we're even worrying about hard disks. You know, the way of the world is moving towards SSDs and stuff. But the cost, there's a real cost differential there, which is quite scary. Now, the prices may drop there, but you saw in the last year that memory prices just rocketed and put the price of whole systems up because the fabrication capacity simply wasn't there. So it's a bit scary that, and the other thing which you have to understand is that these storage technologies, both disk and tape, are relying on relatively few vendors. So there's a market which is relying on 2 or 3 people in each area, and so it's highly sensitive to the way that they organize. And the cost of buying into fabricating these things is huge. I mean, the cost of a new fabrication plant for flash disk is of the order of $15 billion. So this is not something that, you know, a startup can jump into. So, I mean, there clearly are technologies coming, but it's not clear that they will deliver at the scale that we need on this time scale.
I have a couple more questions which are more specifically related to, they will be for Michael, I guess, because I think you already have solved these 2 issues. One is, it's been a long way since we started to use punch cards to now regularly analyze a million spectra in optical astronomy. But are we doing enough effort to researcher, the new 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 researchers, 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 researchers,
depending on your science goal. And some people need, the highest resolution, and they.
Yeah, I may have glossed over how easy it was. Issue because the amount of the reduction.
Number of orders of magnitude.
The simplest would actually be you're going for something that's a time cycle thing to do 1 cube at roughly 6 hours or something like that. So that gives you the biggest.
Yeah, well, I was thinking in terms of public databases where they actually
data sets, and so.
Produce data products which have already had the averaging is general access to go back.
As opposed to the sort of analogy with HSE. Every couple of years they do a complete reprocessing of everything in the archive. We're probably going to do that. But what you produce these for the store, the cubes, and so if you from those